Welcome to Chapter 4, Part F in the EE111 lecture series. We will finish off Chapter 4 in this video, and we're going to talk a little bit more about Thevenin and Norton equivalent circuits, on how to handle dependent supplies with Thevenin and Norton equivalents. We're also going to talk about the superposition technique and how we can use it to solve for unknowns in a circuit. So last time we talked about Thevenin and Norton equivalent, and the way we analyzed Thevenin and Norton equivalency was we would measure the open circuit voltage, which was the Thevenin voltage, the short circuit current, which was the Norton current, and can also be used to find the Thevenin equivalent resistance, which is the same as the Norton resistance. And then we also showed at the end a shortcut that we can do, a way that we can measure the equivalent resistance directly by setting all of the sources in our system to 0, and then finding the equivalent resistance seen by the terminals. Well, that doesn't actually quite work when that trick to find REQ doesn't really work when we are working with dependent supplies. And the reason for that is dependent supplies can sort of transport information about resistances from one part of a circuit to another in a way that sort of changes the resistance calculation. So, for instance, consider this circuit here. If we were just looking with the traditional REQ calculation, this is a current supply. We could set it to a 0 amp current supply, which is just taking it out. So we'd take that out, and then all we'd have left is a 25 ohm resistance. So we could say REQ is 25 ohms. That's not actually going to work though. And you can think about why that's not going to work just by kind of casually examining what's happening in this circuit. Notice we have this 2 kilo ohm resistor over here. That's disconnected from this part of the circuit, right? These two parts of the circuit are totally disconnected. There's this current IX is 0. But as this resistance changes, so changes this current. And this current, or this current here, is a function of this current here, which means that as this resistance changes, the current that flows through this side of the circuit will also change. So it's obvious that that resistance on this other portion of the circuit has an impact on the portion of the circuit where we're measuring the equivalency with respect to those two terminals A, B. It's just not one that shows up by doing a direct resistance equivalent calculation. So we have to do something a little bit different for dependent supplies. The nice thing about Thevenin and Norton equivalents, though, even with dependent supplies, is we can always do the open circuit voltage, short circuit current analysis on these. The only thing that changes for dependent supplies is finding that shortcut to find the REQ. So let's go through it. Let's just solve for an example circuit with dependent supplies. Let's solve for all three: open circuit voltage, short circuit current, and REQ. And also keep in mind, we didn't have to solve for all three. We only have to solve for 2 out of these 3, whichever's easiest for us. Solving for 2 out of these 3 tells us all we need to know about the equivalent circuit. But I just want to show you how to do all 3 for dependent supplies. Okay, so let's just do the analysis here. So let's first of all find the open circuit voltage. So to find VOC, which is equal to the Thevenin voltage. Well, in this circuit here, if we leave these terminals open circuited, the VOC, which is right here, is going to be the voltage across this 25 ohm resistor. And it's interesting to note that's labeled V already in this circuit, and it's a part of this supply over here. So we have to keep that in mind. But it doesn't really matter. What we're solving for is V, which is equal to VOC, which is equal to V Thevenin. So it's actually kind of works out fairly well for us. So we're solving for V here. How are we going to do it? How are we going to solve for V, this voltage across the 25 ohm resistor? Well, we have a current supply and a resistor in series with each other. So, and you might not think they're in series, but remember, there's no current flow through here. So that's basically like a disconnect there. I don't know why they show it. They just show it. So, you know, if I have a current supply and a resistor, I'm just going to use Ohm's law, right? So I can just say V25, which is equal to V, which is equal to, you know, of course, all this as well. That's just going to be, my current here is 20I, and that current is flowing. Now we got to be careful because that current as labeled, that 20I is flowing into the negative terminal, the negative labeled terminal. So we have to use V is equal to negative IR version of the equation, which is equal to negative 20I times 25 ohms. So that is going to be negative 500I. Okay, now it's just what's I? So I is this current here. How are we going to find that? Well, what's the current through that resistor? It's the voltage on this side minus the voltage on this side. So that's going to be, divided by 2 kilo ohms. So I is going to be 5 minus 3V divided by 2000. Yeah. Okay. So that's easy enough. That's our I. The good thing is this V is the same V that we had over here that we were solving for. So we essentially have two equations now. We have V equals negative 500 I, and we also have I equals 5 minus 3V divided by 2000. So let's just do a little substitution, that I in there, and we get V equals, it's going to be negative 2500 divided by 2000. Let's see, minus or a plus actually 1500 V divided by 2000. So I hate fractions, so let's multiply it by 2000. 2000 V equals negative 2500 plus 1500 V. So another way to put that is that, let's see, 500 V equals negative 2500. V equals negative 5 volts. Okay. So V equals negative 5 volts. So that is our Thevenin. I hope I didn't get something backwards here. Just double check myself. Looks okay. All right. So V is equal to negative 5 volts, and that's our VTH. Okay. So next one. Now we're going to find the short circuit current. So we're going to say, what's this current here when we short these terminals? Well, when we shorted these terminals AB, we now put this 25 ohm resistor in parallel with a short. So what happens when we put something in parallel with a short? Out, right out. So now we have this unknown current, the I short circuit, is because we have two 20I flowing this way. We're solving for the current flowing from terminal A to B. So the short circuit current is just going to be negative 20I in this case. And what's happening over here? Well, once again, we have I equals 5 minus 3V divided by 2000. But what's V? Well, V is still the voltage across that resistor, which is 0. Right? We shorted the terminals, which made V 0. So now we're just left with I equals 5 divided by 2000, which is going to be 1 divided by 400. And we can plug that back into here. So that's going to be times. So I get negative 0.05 amps. That's negative 50 milliamps. That's my short circuit current. Perfect. So now, I found the open circuit voltage and the short circuit current. That should be good. But, and now I can find RTH right now. I can find RTH by basically just saying, remember, RTH is equal to VOC divided by ISC. So going back to our last problem, that was -5 divided by -0.05, which is 100. So it should be that my Thevenin equivalent to this circuit should be a 100 ohm resistor in series with a -5 volt supply. I'm getting sloppy. My handwriting's getting sloppy. I apologize. Keeps you on your toes, though. Now you got to pay attention if my handwriting is atrocious here. I'll try to clean it up for the rest of the video here. So this should, I know this already, but let's find this directly. Again, this is a weird case where our RTH was 100, but if we had analyzed this using our traditional method for finding REQ, we would have found that REQ is equal to 25 here. Okay, now let's find REQ directly using the technique. And we're going to use the version of the REQ technique that's required for dependent sources. With dependent sources, we still take out all of our independent sources. So this one, we set that to 0. What's a 0 volt voltage supply? It's a wire. So this becomes a wire through here. But the problem is, if we have a, again, we have to take into account the effect of these dependent supplies. These dependent supplies have this ability to essentially transmit the effect of resistors in remote portions of a circuit into portions of a circuit that doesn't allow us to directly sort of translate these resistances. So there are some techniques that some people use that sort of do fairly complicated transformations of these resistances and insert the transformed resistances into places where the dependent supplies are. And doing that, you can actually just calculate the resistance directly, but we're going to skip. That's actually, I think, more difficult than the approach we're going to take. So the way we do it is we do it with a test voltage or a test current. So we take our circuit, we remove our independent supplies, as we've done here. We set them to 0. And then we apply a test, either a test voltage or a test current. And we get to pick what that voltage or current is. And the idea here is we apply a test voltage. And if we apply a test voltage, we calculate the current. And we treat it just like it's a resistance. We say, if I applied 100 volts to something and I got 1 amp of current, well, that's like I have 100 ohms of resistance. If I apply 5 volts to something and I get 20 volts, that's like I have and I get 20 amps, that's like I have 1/4 of an ohm of resistance, and so on, right? You get this idea that we can't just combine resistances, but we can test the resistance by applying a voltage and calculating the current, or by applying a current and calculating the voltage. And the nice thing about this is we get to pick the voltage or current that we use. So really, we kind of want to pick whatever makes the math easiest for us. I tend to like things with the number 1 because I prefer to do math with the number 1. So let's do that. Let's just apply 1 volt here. So if I apply 1 volt to this system, I immediately know this voltage V is 1 volt. That means I know that this is a 1 right here. I also know that if there's 1 volt here, what's this current? If there's 1 volt across the 25 ohm resistor, the current through the 25 is going to be 1 volt divided by 25 ohms. That's going to be 40 milliamps. So 0.04. Okay. All right. So now we're going to calculate again. This voltage supply is gone. We're going to calculate this current I. What's I going to be? Well, we got a 3 volt supply here. So essentially we have, basically we have 3 volts like this, 2K. Our question is, what is I? Well, we know we have 3 volts across the resistor oriented like this, based on the supply. But we also know that voltage is, as labeled, our unknown I is entering the negative terminal of that voltage across the resistor. So we have to use V is equal to negative IR. So we have 3 is equal to negative I times 2K. I is going to be equal to negative 3 divided by 2K. That's going to be negative 1.5 milliamps. Okay. So now we have, this is 20 times that. So 20I is going to equal 20 times negative 1.5 milliamps. 20 times negative 1.5 milliamps is going to be negative 30 milliamps. So my current flowing down here now is going to be negative 0.03. So what's my overall current here? So I applied 1 volt. My question is, what's the current flow through my 1 volt that I applied? Well, we had negative 0.03 flowing that way and positive 0.04 flowing down that way. So we can say the current flowing in is equal to the sum of the currents flowing out. So my current I is going to be 0.04 plus negative 0.03 equals 0.01. But more importantly, if I applied 1 volt and I got 10 milliamps of current, what's that equivalent resistance? So to make myself a little more space up here, I can say 1 volt equals REQ times 0.01. REQ equals 1 divided by 0.01 equals 100. So 100 ohms is REQ. That's what we found before. In this case, we're just calculating it directly by removing the independent sources, leaving the dependent sources there, but applying a test voltage. We could have done it with a test current, and finding the resulting current if we applied a test voltage, or voltage if we applied a test current. And that's all there is to it. So not, is that easier than just finding the short circuit current and open circuit voltage? It's about on par. This is not as much of a shortcut as is the case with all independent supplies. That's usually finding REQ. That's a pretty quick way to do it. That's a pretty nice shortcut. Maybe it's not quite as big of a deal here. And again, as I said before, I'm more likely to use I'm more likely to use the open circuit voltage short circuit current technique when I'm working with dependent supplies for this reason. But if we want to find REQ directly, this is the way we do it. This is the shortcut that we would take to do that. So one more topic I want to talk about, and that is maximum power transfer. So one of the things, it's a little weird when we talk about Thevenin equivalent, because we say, oh, what's the equivalent with respect to these 2 terminals that are sticking out of the circuit? And it doesn't always make sense why we have these 2 terminals sticking out of our circuit. What do those 2 terminals mean? And one thing we talked about earlier is usually you're connecting something to those terminals. So we do Thevenin equivalent when we want to analyze the behavior of a circuit with respect to 2 terminals, keeping in mind that most likely those terminals are going to be connected to something later on or something else. And one important question we ask ourselves is, what resistance can we connect to those terminals to result in maximum transfer of power to that resistor? So that is to say, what load resistor could we connect between those terminals AB to where we're going to have maximum power dissipated by that resistor based on the structure of the circuit? Now let's think about this for a sec. So anytime I'm told, okay, apply a resistor, or apply a resistor to these things and try to maximize something, my first thought is going to be, let's go to the extremes. Let's try a 0 ohm resistor. Let's try an infinite ohm resistor and see if one of those 2 extremes is where we find our maximum power. Well, let's consider the case where RL equals 0. What's the power dissipated by this resistor when the resistance is equal to 0? Well, we know that power is equal to I squared R, and in this case, I is going to be VTH over RTH, so I is going to be finite, but R is 0, so it's going to be 0. So in the case of resistor 0, the power is going to be 0, unfortunately. Now let's try the other case. So say unfortunately, like I was hoping it would be something other than 0. I don't know. Let's try another case. Let's try the case where RL is equal to infinite. So when RL is equal to infinity, well, we know that power is also equal to V squared over R. And what's the voltage across this going to be? It's going to be VTH. So power is equal to VTH squared divided by infinity. And once again, that's 0. Okay, so off at infinity, we also have a big goose egg for power. Now that might seem silly, this exercise that I just did. I just tested a load resistor of 0 ohms and I tested a load resistor of infinity ohms. But this actually told us something very important. It told us that our maximum power has got to be somewhere between 0 and infinity, and it's not going to be at 0 or infinity. So that means that somewhere between 0 and infinity, we're going to have this point of maximum power. And you might say, well, duh, but it's not a duh. There are many situations where the extremes are where you find the maximum. So sometimes the maximum occurs at the small extreme 0. Sometimes the maximum occurs at the large extreme infinity. So ruling those two out is actually a very important thing to do. But we still don't know where in this curve exactly our maximum power is. Well, the book does a derivation of this. I'm going to skip the derivation for the purposes of this lecture series. If you want to see it, you can look through it in the book. But as it turns out, this resistance where we hit maximum power is RTH. So when we connect a resistor of resistance RTH to a system with a Thevenin equivalent resistance of RTH, we get maximum power delivered to that resistor. So when RL equals RTH, that's when this whole system here delivers maximum power to that load resistor. Why do we care about that? Think about some times where you want to deliver the most power you can to something. When's the time you might want to do that? Well, a lot of times people think, anything where you want more power, right? If you have a heater, okay, a heater is a good case. There's things like antennas, right? Let's say you have a Wi-Fi radio in your laptop and you want to deliver maximum, you'd like to be able to transmit as much power as possible. So that's a case where if you had a system that was powering that antenna, you would want the resistance of the antenna to be matching the resistance of the system that is powering the antenna. So that's actually a very important concept. That's the concept of matched impedance. And matched impedance, well, you'll call it impedance later on, but for now you can call it matched resistance. That is this concept of when you have a powering system coupled to a power drawing system, the way to get a maximum transfer of energy is to have them be matched, have their resistances be matched with one another. And this, again, this is a concept that's going to show up again and again and again. But maximum power transfer, very, very important concept. And you can find it. Its origins come all the way back to EE 111. So you're going to see your senior year or your junior year, you'll be taking classes where you talk a lot about maximum power transfer, where you talk about matched impedance, matched resistance, I should say. And the basis for that comes all the way back to right now. Right now, EE 111 early on, this is where you get that understanding. And you'll see it a lot. If you ever, if you have an old TV with an antenna, you might want to look at that antenna and it'll say something like 75 ohms or 50 ohms or something like that. And that 50 ohms is referring to basically you want for maximum delivery of power from the antenna to the TV or from a radio to an antenna, you want the resistance of that antenna to match the driving or the receiving circuitry of your TV or radio or whatever. So I think I'm doing a worse job of describing this the more I talk about it, so I'm going to stop talking about it. But important concept. Hopefully by me spending so much time blabbing about it, you'll be compelled to believe me that it's an important concept. So, but for the purposes of this class, super easy point. If I'm asking you, what's the resistor you need to connect to this circuit right here for maximum power transfer, you should immediately say, I can find that by just finding the Thevenin equivalent of the system or the Thevenin equivalent resistance of the system, with respect to those two terminals where I'm connecting the thing. And if I find the Thevenin equivalent of that system, that Thevenin equivalent resistance will be the resistance I should connect there to get maximum power transfer. Okay, last concept. We are almost to the end of chapter 4. I don't know why they throw so much stuff into chapter 4. I would have split chapter 4 into like 3 different chapters, right? It could be a node voltage chapter, a mesh current chapter, and then a Thevenin and Norton equivalent. It could be 4 chapters. It could be superposition as a separate chapter too. So superposition is another tool we can use. And just like with Thevenin and Norton equivalent, Thevenin and Norton equivalents were, we're manipulating a circuit, and by doing so, we lose information about the circuit, but it leaves us with a simplified version of the circuit that makes it easy for us to find unknowns when we're looking for a limited number of unknowns, right? Thevenin and Norton equivalent, you don't want to find the Thevenin and Norton equivalent of a circuit if what you're concerned about is finding all the unknowns in the circuit. But you do care if you want to see what that circuit does to something connected to your terminals AB. Similar thing with superposition. Superposition is typically used when you're just trying to find 1 or 2 parameters for a system. You're not trying to solve for all the unknowns. If you are, just use node voltage or mesh current. When you want to find a limited number of things, it can be a useful tool. And superposition is derived from this concept that in linear systems and linear circuits, which all the circuits we deal with in this class, including circuits that have op-amps, which we'll talk about in chapter 5, all the circuits we deal with in this class are linear circuits, and they all have this property as linear circuits where you can identify the impact of each source independently. That is to say, I can tell if I have a circuit like this, I can analyze what the 120 volt voltage supply does to this circuit without worrying that this was 12 amps. And then I could separately analyze what the 12 amp supply does to this circuit without worrying about this 120 volts. So I can basically look at the marginal impact that each source has on my overall circuit. And I can do this source by source. I don't have to analyze the circuit with all the sources in there at once. I can look at the impact of each source independently. That's one of the nice features about linear systems. And that's not just linear electronic systems, linear mechanical systems, linear thermal systems, anything, right? You can look at the impact of each one of these driving sources independently. Okay, what does that mean for us for analyzing? I could say that, oh, you can analyze it independently. That means nothing until we actually show how that's useful for solving a problem. So the idea with superposition is we can analyze a system by breaking it up into pieces. That is to say, we can eliminate one source and then analyze our unknowns, and then we can eliminate the other source and analyze our unknowns. So we can, rather than solving this one circuit that has 2 supplies, we can solve these 2 circuits that each have 1 supply. Now it should be noted, when I took out the voltage supply to get this circuit, I replaced it with a wire. And when I took out the current supply to get this circuit, I replaced it with a break in the circuit. Why did I do that? This is when we remove a source from a circuit, what we mean is we have to set the source to 0. And we already talked about when we found equivalent resistance, setting a source to 0 means a 0 volt voltage supply is a wire. A 0 amp current supply is a broken wire, right? It's a break in the circuit. So we replace current supplies with open circuits. We replace voltage supplies with short circuits. And if we had 3 supplies, if we had, another supply in this circuit here, we can do this. We just would have broken this up into a 3rd circuit. So we would have had a 3rd circuit that only had this supply and left this one open and shorted this one. Of course, we would have had to have the supply worked in here too, but you see what I mean. So we can do this with any number of supplies. We could have 10 supplies, and we can we can just split our circuit up into 10 separate circuits, each circuit only having 1 supply in place, the other supplies being set to 0. We could solve for our unknowns for all 10 of those circuits. And then what do we do to get back to our original unknown value? If we were looking for this current here, so we break it up and we solve for this current, and we solve for this current, and we solve for 10 currents or however many supplies we have. The way we get back to this original current is we just add them all together. So we can take a circuit, remove all the sources but one, solve for our unknown, repeat the process, removing all but a different source, add up those solutions, and the sum of those solutions will be our overall solution to our system. Let's do it. So let's take this same example circuit that I just goobered up with all my writing here, and let's break it up. Let's first analyze this one, and we're going to try to find this current that I had labeled here. Let's analyze this one, and then we'll go and analyze this one. So first circuit through here. To find this current here, the nice thing is we don't have to use node. We could do node voltage. We could do mesh current or something. But I can find this current here just using, you know, voltage divider, current divider. I don't have to go all the way to node voltage or mesh current. Let's do this using voltage divider. How about that? All right. Now I got to be careful with labeling these because I can't just label it I, because I'm solving for this current twice and then I'm adding them together to find I. So I'm just going to call this I1. So looking at this circuit with this open circuit, you know, this is open circuit. So really these wires don't really contribute anything. So my question is, how do I find this current I1 flowing through here? Well, just because this is something that I do in my head, and so I kind of want to show you what I do in my head. Mentally, I would redraw this circuit to look like this. So in my head, this is what I just did. I just redrew the circuit like this. And this tells me that, you know, if I'm trying to find this unknown current I1, which is this current flow through here, what I can do is, if I want to, I can either find the voltage across this whole mess here and then do Ohm's law, or I could find the total current through here and I could do a current divider right here where it splits apart. It's up to me. Why don't we just do a voltage divider? Find the voltage across this mess here and then use Ohm's law to find this unknown current. So to do that, back to basics, let's find the equivalent resistance up here. We have a 2 in series with a 4. We have a 6. That 6 that we just found is going to be in parallel with the 3. That's going to be 2. So we can redraw this circuit as so what's the voltage across the 2 here? Using voltage divider, the voltage across the 2 is going to be 120 times 2 divided by 2 plus 6. So again, it's one of those, I know it, but let's just sanity check ourselves here. 30. So that means we had 30 volts across here. So if we had 30 volts across here, and I'm curious what the current is through this branch resistance was 6 ohms. So I1 is going to be just 30 volts divided by 6, which is going to be 5 amps. Got it. We found I1 once. Okay, now let's do it again. Now this is the second version of the circuit. This one, we left the current supply in and we shorted the voltage supply. So now we're going to find this current again. We'll just call it I2. So in this case, how can we find this? You know, visually, I'll probably flip this circuit 180 degrees. So if it's me, I'm going to rotate this circuit like this. Okay, now if you tell yourself, what? That's not the same circuit, go back and check, because it might not be the same circuit. I could have screwed it up, but I'm pretty sure it's the same circuit. I just wrote, why did I rotate it? I don't know. My brain prefers this circuit to this circuit. So, and I'm trying to find this current through the 2 ohm resistor. So it's pretty obvious to me I'm going to want to do a current divider here. So, and the good thing is the current through this 2 ohm resistor is the current through this entire branch. So I can just find the equivalent resistance to that branch and then find the current through that whole branch, and that's going to be the current through the 2 ohm resistor. So what's the current through this whole branch here? So we have a 3 in parallel with a 6. That's going to be 2. And then that 2 is in series with another 2. That's 4. So we have, so our equivalent circuit now is 12 amps, and we have a 4, and we have a 4. So this current flowing through, and again, this current flowing through this equivalent branch is the current, right? All the current that flows through here has to flow through my 2 ohm resistor. So the current that flows through both of these guys, you know, the current that flows through here is the same as the current that flows through here. I'm not sure it helped by me just, I don't know. So what's this current? Well, it's pretty easy here. We got 12 amps and we got a 4 in parallel with a 4. So I don't have to go through the current divider. I can just say it's going to be split evenly. So I2 in this case is going to be 12 divided by 2. That's going to be 6 amps. So I removed the voltage supply and solved for the one with the current supply. I removed the current supply and solved for the one with the voltage supply. The first time I did it, I got 5 amps for I1 for that current. And the second time I did it, I got 6 amps for that current. So the total current is going to be the sum of those two solutions, which is going to be 5 amps plus 6 amps, which is going to be 11 amps. So that's how we do superposition. And again, we can do this with any number of supplies. We could have had 10 supplies, 100 supplies, and we just solve it 100 different times. What was the advantage of superposition? What was the advantage of doing this? Well, one thing you'll note is this original circuit that I completely goobered up with writing. Maybe I can go back further. Yeah, this original circuit, this is a fairly complicated circuit in the sense that I probably would have had to use node voltage or mesh current to solve this. But you'll notice that when I use superposition, this circuit, I didn't have to use node voltage or mesh current. I was able to just do a voltage divider and Ohm's law. And this one, I was able to do a very simple current divider. So by breaking the circuit up and solving it for each of the supplies and then combining it, I was able to avoid having to use one of these more complicated techniques. And maybe that's going to be better for me. Maybe that's more useful for me. The other neat thing about superposition is, what if we're just curious what changing one supply does to our circuit? Well, if we were going to leave one supply alone and tweak another supply, we could use superposition to find the impact of the first supply and then only solve the simpler circuit for tweaking the second supply and then find the sum total of those resulting values, and that's going to be the overall impact of the circuit. So it's useful in that for that purpose. Superposition is a technique that it used to be very common. So if you talk to an electrical engineer who's over 40 years old, you might find them using superposition a lot to solve for unknowns. And it's useful in a lot of different places. Especially when we get to op-amp circuits, maybe not op-amp circuits in this class, but later on, you see it used a ton as a way to analyze op-amp circuits. Because a lot of times with op-amp circuits, you're saying, I've constructed a fairly complicated circuit, but I only want to know what tweaking this input voltage does to the output. So you don't necessarily care about the other features that you had built into that circuit. You just care about how does this one input change this one output. And in that case, using the superposition technique can be extremely useful. But again, superposition only works with linear systems. A linear system is a system that uses linear amplifiers. Op-amps are linear amplifiers. And I keep saying op-amps. You don't know what those are. Well, you might, but we haven't talked about them. What are not linear things? Diodes are not linear. Anything with a non, I keep thinking diodes. Diodes are not linear. Also, diodes are not linear. Many types of transistors are not linear. There's pretty much any semiconductor device, for the most part, is going to be nonlinear. So unless it's an op-amp. Op-amps are a special case where it's a semiconductor device that is a linear device. But voltage supplies, current supplies, dependent voltage supplies, dependent current supplies, resistors, these are all linear devices. Things like diodes aren't. Okay. What about if we want to do superposition with dependent sources? If we want to do superposition with dependent sources, that's fine. We can still do it. The only thing is we can never take out those dependent supplies. So we can still analyze the system by taking out all of the independent supplies but one. But sadly, we have to leave in those dependent supplies. So it's more work, it's more complicated, but this is still a simpler circuit than this. And this is still a simpler circuit than this, but not by much. So how much are we saving ourselves? But that's how you do it. That's how you do it. So you can't take out the dependent supplies, but other than that, the analysis is exactly the same. So I'm not going to do an example of that. You'll have plenty, or you can look at the ones in the book, but it's just extra. It's basically just extra circuit practice problems, and you'll get plenty of those. So for now, let's be done with chapter 4. It's a great chapter, but it's also just greatly long. And so I'm happy to be done with it. I'm happy that we're out of it. The good thing is, if you're hanging on right now and you're like, holy cow, that video we just had, I don't know what he was doing. I've reached the end. I can't pay attention anymore. You've lost me. We have a reset now. So you're going to do, the last homework out of chapter 4. You're going to get to spend some time with these. So if you're still struggling with these concepts, you're going to get some time going through these. But after chapter 4, we get to take a little step back. We get to do some slightly different things. So if you're reached the end of chapter 4 and you say, that's it, I've given up, that's the limit of my concentration, that's the limit of how much stuff you can fill my brain with right now, give me some time to soak with it, but please stop building on these concepts. The good thing is we're done for a little bit. We're going to take a step back. We're going to switch to talk about some slightly different things. For the purposes of circuit analysis, though, you just got the good stuff. I just gave you the keys to the vault here. Node voltage, mesh current, Thevenin and Norton equivalent, superposition, really great tools that are going to stick with you for your entire time here through this electrical engineering program. You're going to keep coming back to these. You really want to make sure you get these chapter 4 tools really set. But there's light at the end of the tunnel. If you're reaching the limit and you're like, if you put one more technique on top of this, if you tell me one more technique where one of the steps involved is to do a mesh current analysis, I'm going to lose it. I'm going to flip a table. I'm going to flip. Now you're flipping your own table because you're doing this at home. I shouldn't say that. You might be watching this video after 2020. So, but if you've reached your limit, it's all right. We get to stop and take a breather after chapter 4. But still, do the chapter 4 homework. Make sure you understand this stuff. But we're done for now. So as I said, all of engineering is we do something until it gets too difficult and then we switch to a different technique. We have just hit the limit of how difficult it gets. So if we need to analyze systems that are more complex than what I just did in chapter 4, and what we just went over in chapter 4, that's typically where that's the limit of pretty much everybody's level of complexity. So once we hit something beyond that, we switch to a different tool and we solve it a different way. Because for everybody, pretty much, this chapter 4 stuff is about the limit of what we want to have to do with our own brains and our own pencil and our own paper. So if you've made it this far, pat yourself on the back. You've done a great job. Let's be done. We're done with chapter 4. I will see you all in the next video.